Our solution is to combine a recycling system with organic farming practices. The decided method of agriculture, aeroponics, uses no soil or growing medium by suspending the plants in the air and misting their roots. The energy consumption is comparable to hydroponics but requires less water in circulation, which, in turn, allows for easier switching between nutrient mixture and pure water. Roots are able to take in oxygen and respirate freely. The system alternates between two states, resting and misting. The duty cycle is set by the user and the system is required to run constantly to prevent the roots from drying out. Organic farming methods prioritize the health of soil. This is done by avoiding chemical fertilizers and pesticides by using methods that return biological matter to the soil with microbes for processing. The health of the surrounding environment is a priority, and organic farming practices can be followed without directly using soil. Organic nutrient solution and organic pH adjusters will allow the installation to produce organic crops in practice, if not in name.
General system design for this project will outline its fundamental development and structure. Details regarding operations, controls, and hardware are covered in this section. In systems irrigation design, as you can see in the diagram, some solenoids are carefully placed in order to allow all of the system's defined protocols to be carried out. A defined combination of open and closed solenoids will control the water flow such to achieve the desired protocols. The circulation of the water throughout the system is initially set by the pump. Fluids would travel to the atomizers, where the pump could circulate water at high enough flow rate that the mist is consistent and adequate for root nourishment. To reduce the number of solenoids used, Y splitters have been implemented for the simultaneous control of two outgoing channels at once. A manual valve is used to drain the mixing tank at the end of an extended time in circulation. For the internal section, or internal enclosure, it's essential to cover the internal components that are susceptible to light and induce problems, enough to protect them from things such as bacteria, fungi, or algae growth. It's also important to keep things properly sealed to avoid contamination or other foreign intrusions. All acquired parts used have been measured to create proper fittings and therefore seal any leaks that could be another potential source of contamination or unwanted loss in water pressure. The external part of the enclosure will contain only two atomizers used per the size of enclosure to reduce the amount of water necessary for input. Two small vents are used for passive air diffusion, as it's essential for the roots to have enough air in the case of overhumidity, which could be a problem depending on the settings. For the system's assembly, atomizing nozzles are used in conjunction with the solenoids in order to allow necessary operations in the system. There will be two heightened shelves used to realize a gravity-based recirculation system down from the root enclosure to the mixing tank that contains a pump at ground level. These components comprise the irrigation housing for the system. As applications in aeroponics vary, the design may be modified to accommodate different goals. A brief outline of sensor placement can be seen in this diagram. The sensor network used can be seen in more depth in the diagram to the right. A variety of sensors will be used to sense the system's environment for suitable operations in order to achieve the user's desired outcomes. The environmental settings define the parameters taken into account by the MCU. Hence, sensor calibration and testing is critical to the system's functionality. These comparisons demonstrate the sensor selection according to their ability to satisfy the needs of our desired applications. The sensors used are common in irrigation and water controls for things such as pools or liquid dispensing mechanisms. The humidity sensor selected for this project is best suited for small enclosure of humidity such as in aeroponics. The light sensor selected between these two was the APDS 9930. This is due to its higher resistance to humidity. The analog temperature sensor goes to an IC for processing, as it was designed to handle air temperature particularly well. The sensors are selected such to allow easy control of sensor output signals via the use of a multiplexer. Specifications such as operating Temperature ranges, sensing accuracy, and power consumption are considered in the system's design. This level sensor works by conductive triggering. When the desired level is reached, a conductive pin acts as a trigger when enough voltage is felt at the selected pin. To select the water level, the user defines it, and the multiplexer is controlled by the MCU to set that level as the desired level. The system will take into consideration overfilling, as underfilling would only require a notification to the user to add more fluids. To avoid overfilling, the relay controlling the pump will be cut if a pin past the intended one is reached with water. The relay module used in this system is essentially used as an MCU-controlled switch to activate or deactivate a certain part of the system, such as the pump or solenoids. The relays are critical to the system's performance, as they control what part of the system is powered and in what order. To control the 8 channels and any combination desired, a multiplexer will be used to enable the combinations of controls logic from the MCU. The system requires regular maintenance for it to perform as expected. An example would be to drain and replace fluids or recalibrate the sensors, as their prolonged exposure to humid environments could affect its sensing capabilities. A set of states are defined to carry out the necessary tasks by the system. Such tasks include switching from water to nutrient solutions or begin the sensing process.
Thanks, Carlos. I will now discuss hardware components used to implement the systems discussed thus far and their selection. Here is an overview of topics related to the hardware, components, and design used for this project. The microcontroller, level shifter, multiplexer, solenoid, water pump, and relays are all the main major components used to implement the aeroponics system. The power design, schematic, and PCB are the designs themselves. When it came to the microcontroller, there were 3 main contenders: the Atmega 2560, the TI-CC323, and the ESP32ROM32E. The Atmega 2560 is a very popular platform and has up to 86 GPIO pins available. However, there's no native support for Wi-Fi or Bluetooth and is the most expensive of the 3. Then there's the TI-CC323. It natively supports Wi-Fi and Bluetooth, has optional flash memory and internal crystal oscillators, and supports simple link technology, which is very useful in IoT applications. The third is the ESP32ROM32E. It natively supports Bluetooth and can also include flash memory and a 40 MHz crystal oscillator. However, the difference between this and the TI-CC323 is that it is a widely supported platform that keeps even the hobbyists in mind, much like the Atmega 2560. So in the end, we went with the ESP32 due to the fact that it is the cheapest of the 3, while including IoT capability and being a widely supported platform, much like the Atmega 2560. One problem that I ran into was the fact that the ESP32 was a 3.3 volt logic level device. This is problematic with our 5 volt sensors, them being the water flow sensor, the pH meter, and the humidity/temperature sensor. This is due to the fact that 5 volts can't be directly interfaced with 3.3 volts. To address this issue, the NVT1006 PW118 will be used as a level shifter. One main reason for selecting this level shifter is the fact that it is bidirectional and has 6 available channels. One problem that we ran into during the development of this project was the number of GPIO pins required. In order to address this issue, a multiplexer will be used throughout the system. The multiplexer selected is a CD74HC4051E made by Texas Instruments. It will be used to interface 3.3 volt components. The reason why this multiplexer was selected was due to the fact that it is widely supported and highly affordable. In order to implement the irrigation system design, solenoids and a water pump will be used to manipulate solution throughout the irrigation system. When it came to the water pump, there were 2 main contenders: the rule bilge pump and the sea-flow bilge pump. Both ran at 12 volts and both were fully submersible. However, the rule used up twice as much power compared to the sea-flow. In the end, we went with the sea-flow due to the fact that the sea-flow will more than accommodate our needs. When it came to solenoids, we ended up selecting the Adafruit 997s. They run at 12 volts, 320 milliamps, and have half-inch male threading. This is a very important detail when constructing the irrigation system and finding appropriate fittings. To control the 5 volt power line and the solenoids and water pump, solid-state relays will be used. The two solid-state relays used are the CPC 1017 NTR and the CPC 1020 NTR. The main difference between the two of these is that the 1020 is rated for higher current loads. Seen here is a solid-state relay. To the left is an LED, which controls the switch on the right side. When LED is on, the switch is closed. When LED is off, the switch is open. One of the main reasons for selecting these two solid-state relays is the fact that they were the cheapest available on DigiKey that met all the power specifications listed here. Seen here is a block diagram representing the power design for the PCB. The voltage rails on the PCB are 12, 5, and 3.3 volts DC. The 12 volts is supplied by an AC-DC adapter that uses a barrel plug. This barrel plug is then connected to the PCB via a barrel jack. This 12 volt power signal then feeds both LDOs, which are used to supply a regulated 5 volt and 3.3 volt line. The 5 volt line feeds the humidity, pH, water flow, and temperature sensor, while the 3.3 feeds the ESP32 and the light sensor. The level shifter is fed by both the 3.3 and 5 in order to understand the two voltage levels being communicated. The 12 volt DC then also feeds the pump and all the solenoids to manipulate solution throughout the system. Seen here is the schematic for the PCB. To the left are all things power related. At the top is a 3.3 volt LDO, fed by the 12 volt signal from the DC barrel jack. This also feeds the 5 volt LDO, which is controlled via a solid-state relay that pulls the pin low when desired. Then to the right is an array of solid-state relays which will be used to control the water pump and the solenoids throughout the system. Then to the right of that is hardware necessary in order to program the ESP32 via micro USB. To the right of that is a microcontroller itself, the ESP32, connected to a set of female header pins in order to allow for quick prototyping and testing throughout the prototyping stage. Then, at the top right, is a level shifter, also connected to a set of female header pins in order to allow for quick prototyping and testing. Seen here is the first PCB revision. It was done with an EasyEDA due to the fact that EasyEDA is a cloud-based software which requires no software installation. When it came to manufacturing the PCB, there were two main competitors that always came up: Oshmark and JLC PCB. Both are made in the USA. However, Oshmark does offer 2-day turnaround for PCBs. On the other hand, JLC PCB is much more affordable and is streamlined into EasyEDA. Due to the fact that EasyEDA was used as a software to design the PCB, we ended up ordering through JLC PCB due to the fact that it was easy to order from and very affordable.
We've decided to build a web app compared to a phone app for accessibility. A smartphone will be able to interact with a website, but a computer will have more difficulty accessing a phone app. Our application is constructed using the MERN stack. The ease of use and associated speed of its components are the primary motivations behind this decision. The reason why the MERN stack is so easy to use is due to the fact that every component uses JavaScript. MongoDB is a database that stores data as a JSON-style document. Express is a web application framework to complement Node.js. Node.js and React.js are both known for their speed, which respectively handle the back-end and front-end of the web app. Interfacing with a specific system will require a profile. Creating a new profile requires validation that links a user to an installation or designates them as an admin. Through a valid account, creating, editing, or accessing data is handled by the database, such as profile information and the record pertaining to a species of crop being grown. Confirmation is required for everything except pulling data. Controls and environment settings are sent directly to the MCU. Alerts are sent from the system to the user through email, where a stretch goal is to use SMS messages. User information is associated to a primary key that corresponds to a particular system, which, for now, is the prototype. An admin profile can read from every system that has published its data. The individual sets of data are indexed by a foreign key.
Hello everybody. To conclude this presentation, I will go over the bill of materials, our current progress, the roles of each member within the group, and our last remaining challenges. Seen here is a bill of materials for all components ordered thus far. This bill of materials may change as we go throughout the prototyping stage and run into issues that may arise. Seen here is a chart representing our progress on the project thus far. Research is completely done. When it comes to part acquisition, we're just waiting on a few remaining components to come through the mail. PCB design is relatively done and will have a few minor changes throughout the prototyping stage. Software development, testing, and system prototyping are all our main objectives for the next couple of weeks with the upcoming midterm demo. Seen here is a table representing the roles for each member for the project. I primarily focus on the PCB, Carlos primarily focused on hardware selection and design, Seeing focused primarily on firmware, and Chris focused primarily on the web app. Here are the main challenges that we have been facing and will face throughout the remaining of the semester. So far, we need to complete firmware testing and ensure the enclosure assembly is waterproof. On top of this, we need to finalize multiplexer interfacing and ensure that the pH sensor is properly calibrated. If there are any questions, feel free to ask.